Today's lesson is about area of polar graphs. So last time we looked at some basics of polar graphs. The warm-up problem that we would have looked at is the integral from 0 to pi over 3 of the cosine of 2 theta d theta. And the reason that you can pause this to try it on your own. The reason that I want to do this warm-up is because this same problem is going to come up numerous times in our polar problems. So after you've had a chance to work it, we will do it together. So in order to take this integral, you have to do a u substitution. And that u substitution would be that u is 2 theta. So the derivative of u with respect to theta would be 2. So du equals 2 d theta. And 1/2 du would equal d theta. And so we are going to we're going to leave the limits alone. We're going to end up going back to theta and not staying in terms of u. But so we'll integrate from 0 to pi over 3, the cosine of u instead of 2 theta, and then d theta comes out and 1/2 du goes in its place. So the 1/2 comes in front, and then it's cosine of u du. So since the derivative of the sine is the cosine, the antiderivative of the cosine is the sine. So the sine of u, 1/2 times the sine of u, would be evaluated from 0 to pi over 3, except for that we need to change that sine of u back to 2 theta. So it's going to be 1/2 sine of 2 theta evaluated from 0 to pi over 3. So we substitute pi over 3 in for theta, subtract what we get when we substitute 0 in for theta. So do this over here. 1/2 sine of 2 pi over 3 minus 1/2 sine of 2 times 0, which would be 0. So this is 1/2 times the sine of 2 pi over 3 would be the square root of 3 over 2, minus 1/2 times the sine of 0 is 0. So this would be square root of 3 over 4. Now, the important part about this is not so much the limits and what the actual answer came out. It's using the u substitution that we did here to rewrite this as, instead of the cosine of 2u, 1/2 times the cosine of u, and then resulting in 1/2 sine of 2 theta. So this right here is what we probably will be seeing again in our lesson today. So that was just a little preview. Oh. Yes. So what you notice when we did the cosine of 2 theta is that we have a 1/2 out in front, then it's the sine of 2 theta. So now, another thing that we're going to have to recall from last year is some formulas that you learned in trig. Those are called the power reducing formulas. There were 2 of them, and they're going to come up over and over again in our lesson. The sine squared of u was equal to 1 minus the cosine of 2u over 2. And, the cosine squared of u was equal to 1 plus the cosine of 2u over 2. So notice they give you the exact same thing, sine squared and cosine squared, except for the sine has a minus in it and the cosine has a plus in it. But they both change into cosines of 2u. We will be using these. You probably want to put those on a note card and study them because they are going to come up a lot and you do have to know them. So the formula that we're going to start with today is how to find the area of a polar curve. So this will go on a note card as well. The area of a polar curve is equal to the integral from a to b of 1/2 r squared d theta. So we will look at how that comes into play as we do our examples. So let's get started. The first that we're going to do today is we're going to find the area of the polar curve r equals the sine of, 4 theta. Okay, so from last time's lesson, you should be able to tell me what that graph looks like. This is the graph of a rose curve. It has 8 petals. If we were to graph it, well, we could look to see when the radius is 0 by solving 0 equals the sine of 4 theta. So to solve for theta, you do the inverse sine of 0 equals 4 theta. Do the inverse sine on both sides to cancel that sign. So inverse sine of 0, when is the sine function equal to 0? Well, that occurs when the angle is 0, or also when the angle is pi. And you could add the period of the sine function to that any number of times. So 2 pi n. That equals 4 theta. If you'll remember from solving trig equations, the 4 affects the period, so we divide both sides by 4, divide everything by 4. Everything gets divided by 4. So you get 0 pi over 4, and then you're adding, see, 2 over 4 would be 1 over 2. So this would be pi n over 2 equals theta. So basically, adding pi over 2 to each of these, if you add pi over 2 to 0, you're going to get pi over 2. So you've got 0, then pi over 4, then you've got pi over 2. And then if you add pi over 2 to pi over 4, you get 3 pi over 4. And if you add pi over 2 to pi over 2, you get pi. And it goes on and on and on like that. That's going to be the solution. So that means that when the angle theta equals 0, we are at the pole for our polar curve. Then it loops around, and when theta equals pi over 4, we hit the pole again for the next time. And then it's going to produce 2 petals in each quadrant that are the same. So this right here is what I'm going to start finding the area of. And then since there's a total of 8 petals, that's double this 4, we're going to just find the area of the one polar curve and then add it 8 times, or multiply it by 8. So my area is going to equal 8 times the integral from. The lower and upper limits of the integral are the theta values when I'm hitting that pole where I'm starting and ending, finding that area from. So I'm starting at 0 and I'm going to pi over 4. And then I'm using that same formula that we just did the note card for, 1/2 r, and the r is this, r equals equation. So sine 4 theta squared d theta. So this is how I'm going to find the area of the polar curve. Setting it up is probably the hardest part. We've got this one set up, so now we just need to evaluate the integral. You might have to do this with or without a calculator. I would probably practice more of them without, because it's not very hard at all to do it with a calculator and you want to get your practice. So I'm going to move to the next slide to work this out. Area equals 8 times the integral from 0 to pi over 4 of 1/2 sine 4 theta squared d theta. So the first thing I want to do is pull that 1/2 out in front. So 8 times 1/2 is going to be 4 times the integral from 0 to pi over 4. And then I'm going to square the sine function, so I'm going to go sine squared of 4 theta d theta. Okay, so this is why I need the power reducing formula. Remember we said that the sine squared of u was equal to 1 minus the cosine of 2u over 2. So I am going to do a replacement here. Substitute the power reducing formula in here, so that's going to be less u function stuff for us, u substitution stuff for us to do here. So I'm taking out sine squared of 4 theta and I'm replacing it with, I'm going to do 1/2 instead of divided by 2 since I'm integrating. So that's 1/2 times 1 minus the cosine of 2 times u. What is our u for this one? It's whatever the argument of the sine squared was. That's 4 theta. So 4 theta goes here. And then I've got d theta. Okay, so I'm going to pull that 1/2 out in front with the 4. So that's going to be 2 times the integral from 0 to pi over 4 of 1 minus the cosine of 8 theta d theta. Now, I'm going to go ahead and integrate. And thinking back to our warm-up, we're going to use that to do that second term. We're going to have 2 times the integral of 1 is theta with respect to theta, minus, if I am taking the integral of cosine 8 theta, let's see, I wonder if I can flip back to that warm-up. Okay, I think I'm still recording correctly. So cosine of 8 theta will be replaced with 1/8 sine of 8 theta. Okay, and we're evaluating this from 0 to pi over 4. So we're going to substitute pi over 4 in for both the thetas, then subtract what we get when we substitute 0 in for both the thetas. So this is the arithmetic part of it. 2 times pi over 4 minus 1/8 sine of 8 times pi over 4 minus 0 minus 1/8 sine 8 times 0. So this is 2 times pi over 4 minus, this is the sine of 2 pi, which is the same as the sine of 0. So 0 minus, the second set of parentheses here, I've got 0 minus the sine of 0 is 0. So this is all 0. So it's basically just 2 times pi over 4. 2 times pi over 4 is equal to pi over 2. So that's the answer for the area of the Rose curve that we started with the equation r equals sine of 4 theta. Remember, we multiplied it by 8 to begin with, so this is all 8 petals. Okay, so we've just finished our first example. Now we're going to move to the next one. Example 2. The equation is r equals 5 times the cosine of 2 theta. So this, you should know from last time's lesson, is another Rose curve. This one has 4 petals. You can see when it hits the pole by setting 0 equal to the equation 5 cosine 2 theta. So divide by 5 on both sides, 0 equals the cosine of 2 theta. And take the inverse cosine on both sides to get 2 theta by itself. When is the cosine equal to 0? Well, that is the x-coordinate, so that's along the vertical axis. So that's going to be at pi over 2, and then at 3 pi over 2. Adding the period onto that, the period of the cosine is 2 pi n. And then we have to divide by 2 to get theta by itself, so we divide everything by 2, or we might want to think of multiplying everything by a half. So pi over 2 times a half would be pi over 4. 3 pi over 2 times a half is 3 pi over 4. And then we're adding multiples of pi n. Okay, so we're going to think about this polar curve. Remember, the symmetry on the Rose curve that has a cosine for equation is the petals overlap the x-axis here. So we are at the pole for the first time at theta equals pi over 4. But at theta equals 0, we are right here at 5. This is exactly a half of a petal. This is a 4-petal Rose curve. So what I could do is find the area of this half petal and then multiply it by 8, because that would fill in the other half here, and then you'd have 2 halves here and 2 halves here and 2 halves here. So if I find the area of this half petal, then I can multiply it by 8. So we're handling this one a little differently. Alright, so let's write the equation. It's going to be 8 for the area. 8 times the integral from theta equals 0 to theta equals pi over 4 of 1/2 times r, which our r equation is 5 cosine 2 theta squared d theta. And now that's what we need to work out in order to find the area. I'm not going to go through this one all the way to the end again. I'm just going to get you to where you'd be ready to rock and roll. So I'm going to pull the 1/2 out. So that's going to be 4 times the integral of pi over 4 times, this time the 5 gets squared, so it's 25 cosine 2 theta d theta. The 25 can come out in front. So it's going to be area equals 100 times the integral from 0 to pi over 4 cosine squared 2 theta. Oh, look, I don't have y'all to yell at me that I made a mistake on the last line where I had the 25 cosine. That should be 2 theta. If you're copying what I did, please fix that. So cosine squared 2 theta d theta. Now I have to use the power reducing formula to write this without the square. I'm running out of space, but I don't really want to advance to the other slide. I'm going to draw a little line and come over here to the left. So if I'm using the power reducing formula, it's going to be area equals 100 times the integral from 0 to pi over 4, and then cosine squared 2 theta will become 1/2 times 1 plus the cosine of 2 times u, which is 2 theta d theta. And now that 1/2 can come out in front, and I'll have 50 times the integral from 0 to pi over 4 of 1 plus cosine 4 theta d theta. And the way you would work that would be just the same way that we did on the last one. Like I said, the harder part here is getting it set up and then manipulating it so that it is integrable, our favorite word, integrable, by using the power reducing formula to get rid of that square. Alright, so here's example 3. We are going to find the area of the polar curve represented by the equation r equals 3 plus sine theta. So you might recognize this to be the equation of a limacon, convex. So the line of symmetry is along the y-axis. It goes down here, down to 1, up to 4, 3, sorry, right, left. Here we go. It's kind of a blobby looking line. So our limacons are some of the easier ones to find the area of. You're just going to go from 0 to 2 pi, so like a whole circle of 1/2 times the r equals equation 3 plus sine theta squared d theta. And so we can go ahead and work this one out. It's not too bad. Pull the 1/2 in front. We're going to go ahead and square this quantity, which means we're going to FOIL it out. So 3 squared is 9, plus twice the product of the first and last term. So 3 sine theta and 3 sine theta would make 6 sine theta, plus the last term squared, sine squared theta d theta. And now we do need to use the power reducing formula for this sine squared theta. So we're going to have all the same stuff followed by 1/2 times 1 minus cosine 2 theta, then d theta. Now, I want to split this into 2 separate integrals so that I can pull the 1/2 out in front of that second piece. So I'm going to handle this part as one integral and this part as a separate integral. So it's going to be 1/2 times the integral from 0 to 2 pi of 9 plus 6 sine theta, plus, for the other one, I still have the 1/2 out in front, but I also have this additional 1/2 pulled out front, so it's going to be 1/4 the integral from 0 to 2 pi of 1 minus cosine 2 theta d theta. So when I integrate this first one, it's going to be 1/2 times 9 theta minus 6 cosine theta, evaluated from 0 to 2 pi. And the next one is going to be 1/4, plus in the middle, 1/4 times theta minus, and this is where we're going to use that same thing like we did on the warm-up. It's going to be 1/2 sine 2 theta, evaluated from 0 to 2 pi. So now I'm just going to plug in my 2 pi's and subtract what I get when I plug in my zeros and work out all that arithmetic I'm going to move to the next screen to do that. It's going to take a bit of room. So I've got 1/2 times 9 times 2 pi minus 6 cosine of 2 pi I need another set of parentheses around that whole thing, minus 9 times 0 minus 6 cosine, oops, that's supposed to look like a cosine, of 0 plus 1/4 of 2 pi minus 1/2 sine 2 times 2 pi, so 4 pi minus 0 minus 1/2 sine 2 times 0. Yeah, that's a lengthy one. Might have to turn your paper sideways for this one. So now we've got 1/2 times 18 pi minus 6 times the cosine of 2 pi. The cosine of 2 pi, that's the same as 0, would be 1. So that's just minus 6. Minus 9 times 0 is 0. Minus 6 times the cosine of 0. The cosine of 0 is 1. So that's minus 6. Plus 1/4 times 2 pi minus, we have sine of 4 pi here. The sine of 4 pi is same as sine of 0, which is 0. Minus 0 minus sine of 2 times 0. The sine of 0 is 0. So I have 1/2 times 18 pi minus 6. Then I have minus negative 6, so that's going to be plus 6. Plus 1/4 times 2 pi minus nothing. So this is going to be 0 for those. 1/2 of 18 pi is 9 pi plus 1/4 of 2 pi. 2 pi over 4 would be pi over 2. I can get a common denominator, which I really already had. 18 pi over 2 plus pi over 2 makes 19 pi over 2. And that is the answer to that problem. Okay, next we're going to move on to finding areas of intersections of polar curves. So, when we find the area of the intersection of a polar curve, we are looking at, say, a situation where perhaps we have excuse me, a circle and then a rose curve. And so there's this area that overlaps. You're going to have two R equations, R sub 1 of theta and R sub 2 of theta. And they're going to have an intersection point on each side. So this theta would equal A, and this theta would equal B. So the way you're going to find that area is to take the integral from A to B, so the theta where they first meet to the theta where they second meet, of 1/2 times, normally it's r squared, but this is going to be your outer r sub 1 of theta squared minus r sub 2 of theta squared d theta. All right, so this is another note card. So example 4, we're going to find the area inside r equals 9 cosine theta and r equals 9 sine theta. So that's going to be like the overlap of these two. So first I want to make a sketch, and that's often a helpful thing to do on these, which is why we did our graphing lesson last time to practice on this. These equations are both circle equations. They both have a diameter of 9. The cosine one lies with the x-axis as its axis of symmetry, and the sine one lies with the y-axis as its line of symmetry, so it goes out 9 here, out 9 here on the other one. They both meet at the pole, and they have this region here that overlaps. Now, where do they overlap? That's going to be at the angle theta equals pi over 4 because of the symmetry that's going on here. It goes right through the middle of the quadrant. So if I want to find the points of intersection, it might not always be that I can tell by graphing. You can set them equal to each other. 9 sine theta equals 9 cosine theta. Divide by 9 on both sides. Sine theta equals cosine theta. If you want to solve for this, you could divide both sides by the cosine of theta. Sine over cosine is tangent of theta equals 1. And then if you take the inverse tangent on both sides, theta equals the inverse tangent of 1. So pi over 4 is equal to theta. Theta equals pi over 4. We're only working in the first quadrant here because of the situation we're dealing with. So, what I could do on this particular example is I could find the area that it falls inside just one of the circles from 0 to pi over 4. My picture is not very good. Let me see if I can clean this up a little bit. So this area right here is going to be inside of the sine circle equation. It starts at 0 and it goes up to pi over 4. So if I find that area and double it, that's going to be the area of the intersection for this one. So it's going to be 2 times the integral from 0 to pi over 4 of 1/2 9 sine theta quantity squared d theta. So that's what I would be finding the area of to get me this overlapping region. So pull the 1/2 out in front. Now I've got the integral from 0 to pi over 4 of 81 sine squared theta d theta. I can use my power reducing formula on the sine squared, and I can pull my 81 out in front. So 81 times the integral from 0 to pi over 6 of, for the sine squared, that's going to be 1/2 times 1 minus the cosine of 2 theta d theta. So the 1/2 can come out in front. So I've got 81 over 2 times the integral from 0 to pi over 6 of 1 minus cosine 2 theta d theta. I'm going to have to go to the next slide. So that's going to be 81 over 2 times, if I integrate the 1 I get theta, minus integrating cosine 2 theta is 1/2 sine 2 theta, and this is evaluated from 0 to pi over 4. So it's going to be 81 over 2 times pi over 4 minus 1/2 sine of 2 pi over 4, which is the same thing as pi over 2. And then minus 0 minus 1/2 sine of 2 times 0. So 81 over 2 times, this will be pi over 4, the sine of pi over 4, square root of 2 over 2. Oh wait, 2 pi over 4, sorry. Sine of pi over 2 is 1, times 1/2 is 1/2. So pi over 4 minus 1/2, and this second one with the sign of 0 is just 0. So I can distribute my 81 halves and make it be 81 pi over 8 minus 81 over 4. You could multiply that second fraction by 2 over 2 to get it all as one fraction, but this is actually the way they left it when they did it. So, next example. Example 5. We're going to find the area inside the cardioid r equals 1 plus sine theta, and outside the circle r equals 1. So, graphing these, I've got a cardioid 1 plus sine theta. So that means it's going to intersect the x-axis at 1 and at -1. It's going to go up to 2 on the y-axis, and it's like an upside down little heart shape-ish. Then the circle has a radius of 1 centered at the origin, so it goes up 1, down 1, left 1, and right 1. So I want the area of the region that's inside the cardioid but outside the circle. So that's going to be this little crescent shape that we see up here at the top. So this is the one where we're going to use that formula where we subtract the two r's in the equation. We want to see what is the theta for each intersection. Well, I can see clearly from my graph that they intersect at 0 and pi. So that's an easy one. If you're not sure, of course, you set them equal to each other to find their points of intersection. Then we have 1/2 of the big R, which is the outer one, which for this problem is the cardioid, 1 plus sine theta squared, minus the smaller interior curve, which is the equation r equals 1, so that's just going to be 1 squared d theta. So the 1/2 can come out in front. 1/2 the integral from 0 to pi. I'm going to square 1 plus sine theta, so that's going to be 1 plus 2 sine theta plus sine squared theta minus 1 d theta. I do need to use the power reducing formula. Oh wait, first I could combine like terms. +1, -1, those add up to 0. So now I'm going to use the power reducing formula. So I'm going to have 2 sine theta plus sine squared theta is replaced with 1/2 times 1 minus the cosine of 2 theta d theta I'm going to split this into two separate integrals so I can take care of that 1/2 a little easier. So it's going to be 1/2 times the integral from 0 to pi of 2 sine theta d theta plus 1/4 times the integral from 0 to pi of 1 minus cosine 2 theta d theta. So now the 2 could come out in front here also. 2 times 1/2 is just 1. So all I'm integrating here really is sine theta. So that's going to be negative cosine theta evaluated from 0 to pi. And here I'm going to have plus 1/4 times integral of 1 with respect to theta will be theta. And the integral of negative cosine 2 theta is going to be negative 1/2 sine 2 theta. And that's evaluated from 0 to pi. I'm going to go to the next screen to do some arithmetic. Negative cosine pi minus negative cosine 0 plus 1/4 times, plug in pi, minus 1/2 sine 2 pi minus 0 minus 1/2 sine 2 times 0. And now I'm going to do these. Negative cosine of pi is 1, plus the cosine of 0 is also 1, plus 1/4 times. Okay, the sine of 2 pi is the same as the sine of 0. That's 0. And also over here, the sine of 2 times 0 is 0. So that's 0. So in the parentheses, all I should have is pi. So that's 2 plus 1/4 pi, or pi over 4. 2 plus pi over 4 is the answer. Okay, we have one example left to do. But before we get started on that one, I just want to tell you a little bit about the homework. For the homework assignment, there's a total of 13 problems. Some are what I would consider easy, others are what I would consider quite challenging. I would say try to do them without a calculator because you need the practice. And definitely draw pictures of your graphs and plan on needing to do that without a calculator as well. Problem number 23 is particularly hard, and we're not going to do an example like that, and there's a reason why. You will see some crazy things come up on the AP exam that are different from any we've seen before that you have to use your good problem-solving strategies on. So that's definitely one of those. There's a million different ways that you can set up these area problems, and you need to be able to tackle some challenges. That being said, there's also some very easy ones, so there's some of those in your homework as well. So number 23 is the really hard one in your homework, and if you can't do it, I'm not going to count off for that. We'll just grade it like there's 12. But I would like you to try it and challenge yourself. So number 6, this last example, is one that is of comparable level of difficulty. It's tough, and it takes a lot of room. So we will get going on that. We're going to find the area. Ooh, it's so hard to write with this stylus. Inside the circle, r equals cosine theta, and inside the rose curve, r equals sine 2 theta. So the first thing I want to do is make a little graph of what this looks like. So the circle r equals cosine theta has a diameter of 1, and it lies along the positive x-axis, something like that. The rose curve r equals sine 2 theta has petal length of 1, and it's got a y-axis line of symmetry, there are a total of 4 petals. So the way that's going to be is if you were to look at your pi over 4, negative pi over 4 lines and go out 1 unit along each one. That's what we're talking about right here. And my picture is not very good. Picture's worth 1,000 words. It helps if you draw it correctly. So let me see here. Okay, so what I want to do, if I'm finding the area that is inside the circle and inside the rose curve, it's the overlapping area. So I'm going to look at this overlapping area that I'm marking with red. I'm going to try to find that area, and because of the symmetry, I'm going to just double that because it is also the same down here below. So when I look at this area, I want to find the point of intersection right here. I can see that they definitely intersect at the pole, but I also want to find where do they intersect up here. So I'm going to set them equal to each other to find that. The cosine of theta equals sine 2 theta. You may or may not remember the double angle formula from pre-cal. Those come in handy, especially on a problem like this. Cosine of theta equals 2 sine theta cosine theta. So I'm going to subtract cosine theta from both sides to get this set equal to 0. And then I'm going to factor out the cosine of theta. And I'm going to set each factor equal to 0. So cosine of theta equals 0, 2 sine theta minus 1 equals 0. And solve. So take the inverse cosine on both sides of this one. Where is the cosine? Equal to 0. At what angle? So that's the x-coordinate. So that's going to be theta equals pi over 2. Then, and I know that it also equals 0 again later at 3 pi over 2, but that's not going to come into play working in this first quadrant. We really only need answers that fall either on these quadrant boundary lines or within them. So then the other one would be, if I add 1 to both sides and divide by 2 on both sides, sine theta equals 1/2. The inverse sine on both sides, inverse sine of 1/2 would be theta equals pi over 6. So what I've got is the graphs begin together at the pole, and then it travels out along the rose curve until we get to pi over 6, and then it travels along the circle curve until we get to pi over 2. So we're going to write an integral that will allow us to find the area of both the top section and the bottom section. We're going to kind of split it into 2 regions because we're going to use the rose curve as the boundary line for this first portion from 0 to pi over 6. And then we're going to use the circle curve as the boundary line for this second section from pi over 6 back to pi over 2. So we're going to write 2 separate integrals, one for the top section, one for the bottom section. Hopefully you've got a good picture of this drawn on your paper, because I'm going to scoot to the next slide and then I won't have it to show you while we're working. So we're going to do the top section. Well, let's do the bottom section first. The bottom section of that overlap is going to be the integral from 0 to pi over 6 of 1/2 r squared, and the radius for that bottom section, the boundary, is the rose curve. So sine 2 theta squared d theta. And then we're going to add to that the top section. Why is this not right? Which is going to be the integral from pi over 6 to pi over 2 of 1/2 times r, which the r for the top section is boundaried off by the circle, which is cosine theta squared d theta. So we're adding these two integrals together. Also, once we find that, that's the overlap in the first quadrant. There's an overlap of equal size in the fourth quadrant. So we're going to double all of this. So it's going to be 2 times this whole integral. And let's see, I could pull the 1/2 out in front. Then this would be sine squared 2 theta d theta plus 1/2 times the integral of pi over 6 to pi over 2 of cosine squared theta d theta. Now notice, when I pull that 1/2 in front, or distribute the 2 into the parentheses to both terms, those 1/2s go away. So that's kind of nice. So now I'm just doing the integral from 0 to pi over 6. Oops, I forgot the over 6 on the last one. Pi over 6 sine squared 2 theta d theta plus the integral from pi over 6 to pi over 2 of cosine squared theta d theta. All right, I need to use power reducing formulas for both of these integrals. So the power reducing formula for sine squared of 2 theta is going to be 1/2 of 1 minus the cosine of 2 times 2 theta, so 4 theta d theta, plus the integral from pi over 6 to pi over 2. Power reducing formula for cosine squared of theta is going to be 1/2 times 1 plus the cosine of 2 times theta d theta. So those 1/2s can both scoot out in front of their respective integrals, and then we can integrate that which is in the parentheses from both of these integrals. So it'll be 1/2 times the integral of 1 is theta minus the integral of cosine 4 theta is 1/4 sine 4 theta, and that is evaluated from 0 to pi over 6, plus the 1/2 out in front times the integral of 1 is theta plus the integral of cosine 2 theta is 1/2 sine 2 theta, and this is evaluated from pi over 6 to pi over 2. So now I plug in my upper limit, subtract what I get when I plug in my lower limit. So 1/2 times pi over 6 minus 1/4 sine 4 times pi over 6 minus, if I plug a 0 in for theta, that's 0, and if I plug 0 into the sine of 4 theta, sine of 0 is also 0, so that whole thing with the 0 is just going to come out to 0. Plus 1/2 of pi over 2 minus 1/2 sine 2 pi over 2 minus pi over 6 minus 1/2 sine 2 pi over 6. Okay, so we're going to plug and chug, do some arithmetic here. 1/2 of pi over 6 minus 1/4. The sine of 4 pi over 6 would be the same thing. That fraction simplifies to 2 pi over 3. The sine of 2 pi over 3 from our unit circle is square root of 3 over 2, and we don't need a minus 0, plus 1/2 of this will be pi over 2. Let's see, the sine of 2 pi over 2 would be the same thing as the sine of just pi. And pi, the sine of pi is 0, so that's going to be minus 0 there. So just pi over 2 for that first set of parentheses, minus, inside the next one we're going to have pi over 6. Then we're taking the sine of 2 pi over 6, which is the same thing as pi over 3. So the sine of pi over 3 would be y-coordinate square root of 3 over 2. So it's minus 1/2 times square root of 3 over 2. So that's going to be square root of 3 over 4. Hang on just a second. I feel like I have a sign error in here. Oh, that's not what you want to do when you're making a video. Pi over 6, square root of 3 over 4 is definitely this quantity. Okay, yes. I made a mistake up here at the very top of this screen when I put theta minus 1/2 sine 2 theta. That should have been theta plus. Here, I'll do this in red so it stands out. Theta plus 1/2 sine 2 theta. It's kind of helpful when all your work flows down a page instead of a little bit here and then a little bit on the next slide. So this should have been a plus here and here, which doesn't affect the pi over 2 part of it, but then minus pi over 6, it should have been plus 3 pi, square root of 3, over 4. All right. Not the easiest problem we've done all this year. In fact, quite the contrary. So we're going to distribute our 1/2, multiply, simplify. So this is going to be pi over 12 minus square root of 3 over, it's going to be 4 times 2 times 2 again, so that's 16, plus, this will be pi over 4 minus, the 1/2 distributes here also, and the negative distributes, so it's going to be pi over 12 minus square root of 3 over 8. So if I want to combine all of these fractions, I need a common denominator. It looks like, well, hang on. The pi over 12 will subtract this pi over 12, and that adds up to 0. Now what's left, I should have a common denominator of 16. So the first fraction already has a 16. This one I can multiply by 4 over 4. And the last one I can multiply by 2 over 2. So this would be negative square root of 3 over 16 plus 4 pi over 16 minus 2 square roots of 3 over 16. And the first term and the last term are like terms, so we can combine those. Negative square root of 3 and negative 2 square root of 3 makes negative 3 square roots of 3. So it's going to be 4 pi minus 3 square roots of 3 over 16. That's the answer to this problem. So, are you going to see many of this level of difficulty? No. But I would not feel like I had adequately prepared you for things that you can be presented with had I not given you one of this level of difficulty. So let's use our good problem-solving skills, put on our thinking caps, and tackle these area problems. You'll find some are very simple, and you'll find some are quite complex. Good luck with your work. Have a great day. Bye.